Attention is all you need. The paper that has taken the NLP world by storm. Today's video is the simplest example that you can find on the internet regarding what self-attention is. So I'll implement self-attention using Python's NumPy package. So without wasting any further time, let's kickstart by importing the necessary modules. So in this exercise, I'll require NumPy. I also need softmax. So for that, I'll use SciPy's implementation of softmax. I'll need Seaborn, and I'll also need matplotlib. Why do I need all of this is something that I'll kind of let you know in the later section. I also want to show you how vectors basically interact in the 3D space so that attention makes a lot more sense, which is where I need something to plot in 3D. So that is what I'm importing currently. Mplot 3D import axis 3D. So these are some of the things that I'll require. I'll quickly go forward and run the cell. Firstly, I'll require 3 inputs, which is what I'll create here. So I'll say input 1 is equal to np.array, a list inside this. So I will put in some random numbers like 1, 0, 1. D type is equal to float 32. Let's take 3 inputs. So I'll have input 1, input 2, and input 3. I'll add some more random numbers here. So this will be say 2, 0, 0. Let's create something that is in the negative direction. So -1 here, -1 again here, and say this is +1. So I have my 3 inputs ready. Now what I'll do next is I'll show you how these inputs look in 3 dimensions. So these are basically vectors, right? 3-dimensional vectors. I have 3 3-dimensional vectors, which is what I'll show you in a 3D space. Firstly, I'll create a figure. Fig is equal to plt.figure. I'll set a size of this particular figure as well. So fig.set size inches. Say 16,8 or maybe 18,10. I think this is a reasonable size. Ax is equal to fig.add subplot 111 and projection equal to 3D. So what I'm doing here is I'm adding a subplot. Just one subplot is what I require, and I want this to be like a 3D projection. Now I wish to show you the vectors in the 3D space, which is where I'll require the function quiver. I'll quickly add the commands regarding quiver. So the way I would go about doing that is ax.quiver. The starting coordinate is 0, 0, 0. So 0, 0, 0. The end coordinate is my input. So either I can add it through the array itself or I can rewrite the entire thing again. So I'll kind of rewrite it. 0, 1, 0 is my first array. I'll add a color to this. So color is equal to red, for example. Similarly, I'll do this for the other vectors as well. So let me remove the spaces firstly. So yes. So this is my second vector. This is my third vector. The second vector can be blue. The third vector can be green. This is 0 to 0. So I'll say 2 here, 0 here, and 0 here. Similarly, this is -1, -1, and 1. So I have everything set up here. The only thing that I want to now have is like a good view wherein I'll set the limits for x, y, and z. So ax dot set x limit. I want it to range between -1 to 2. Similarly, I'll set limits for y and z. So y and z. And finally, I'll call the plt.show function. So these are the 3 vectors that I have right now. Think of these 3 vectors as 3 keywords, right? So I can name this vector as, say, vector king. The input 2 can be queen and input 3 can be mobile. What I'm trying to do right now is I'm trying to find the attention scores for these three words. How the weights would be computed is a different question altogether, but once the weights are computed, what happens and how the attention score kind of helps us understand the relationship between words is what I'll try to unravel in this particular video. So these are my three words: king, queen and mobile. Now for these three keywords, I have a vector representation in 3D. This is not an actual embedding. I've just taken three vectors which represent, say, three keywords. So my first word is basically king, which is this particular red arrow. My blue arrow signifies queen, and this green arrow signifies the word mobile. So there are three different words. King and queen are related to each other, which is what you can see here. If you take a dot product, the value would be closer to 1. So this is something that is very evident from the vectors. How does this translate to attention is what I'll kind of uncover in the upcoming sections. So let's go forward. Now, if you go back to the attention formula, you have attention Q KB is equal to softmax of Q dot K transpose divided by the dimension of the key matrix and multiply the entire thing with the value matrix or value representation that is there, right? How are these values calculated through an input value is what I'll try to uncover in the coming section. So this formula is something that is the basis for the calculations going forward. Let me start the activity by defining the matrices that I require. So firstly, I'll require WQ, which is the query matrix. So WQ is equal to np.array. I'll create a 3x3 matrix. So let me put in some random numbers like say 1, 0, 1. I'll add one more bracket here and I'll end it here. Now I'll create two more rows for this. Let me put in some random values again. So 1, 2, 0 and 0, 0, 1 for example. So query matrix is more of like, hey there, do you have this information? So it's more of a query. So think of query matrix as someone speaking, hey there, do you have this particular information? From the input, you ask a query. The query is there to kind of ask for more information. Similarly, you have key and value vectors as well. So I'll quickly create two more vectors. Firstly, I'll run this cell. Then I'll create two more vectors. So query. Then I'll create key. And then I'll create value. I'll again assign some random values here. So for key, I'll say 0, 0, 1. 1, 1, 0 for example, and then 0, 1, 0. So this is my key matrix. Key is vector at which the query looks to compute weights. So example, if I want an information, the query will kind of ask for that information. Key will tell me that, hey, I have this information. Now give me a larger weight for this particular combination of input query and key, which is where the key representation or key matrix comes into picture. So this is what I have as key matrix. Finally, I have my value matrix. So again, I'll kind of randomly add some numbers here. So I'll say 0, 1, 0, 0, 4, 0 here, 1, 0, 2. So my value matrix is also set up. Now value is basically the weighted sum as the attention output. So query is asking for information. Key says I have the information. Let's multiply and create a bigger weight. Once this combination is set up, then value says, hey, I have the information. Let me share it across as a weighted sum. So this is how I kind of remember query, key and value matrices. Now what I've done here is I've assigned random values. Okay. Now, once you think of predictions, given that I'm taking predictions in this particular example, and given this is a very simplified example of how self-attention works, these weights are learned by backpropagation. So once you share training data, so for example, if you want query, key and value matrices to learn nitty-gritties for a translation task, say for example, English to French, you would feed in English words, and at the decoder's end, you would have the inputs for French as well. Correspondingly, the error would backpropagate and would kind of update the query vector, the key vector, and the value vector. Once the backpropagation is up and running, once you have a fairly accurate representation of the entire translation task, it is here that you can kind of use the entire process like a normal neural network, wherein you pass in inputs, there are a set of multiplications that happen, and you get the final output. So here what I'm doing is I am assuming the last stage to have reached without training. I am kind of showing you the forward propagation step, which is where self-attention will calculate, say, values between the three keywords that we have, that is king, queen, and mobile. If this idea is clear, now I'll go to the other section. So I'll quickly create more cells here. So for every input, you pass that input through all the three matrices, that is your query, key, and value. Okay. Now once these input values are kind of passed through the matrices, you get query representations, key representations, and value representations. Okay. Now say for example, I say print input 1 dot WQ, for example. So you will have something like this. Similarly, for input 2, you will have a value, and for input 3, you will have a value. So this for every input is my query representation. Rather than having 3 steps, I can parallelize the entire process by kind of taking this as an input array and then taking the dot product. So I'll say inputs is equal to np dot vertical stack input 1. Here is an underscore. So input 1, input 2, and input 3. Now if I show you inputs, it's basically a 3x3 array. And now when I take the dot product, so when I now say inputs dot, so this is my query representation for all the 3 inputs. So I have 102, 240, and -2, -2, 0. These representations are something that I require for query, key, and value, all 3 together. Okay. What I'll do next is I'll calculate query, key, and value representation. So I'll say query representations is equal to inputs dot into query. Similarly, I'll have one for key, one for value. So I'll change this to key. This will be WK. This will be value. And I'll say this is WV. If this is clear, I'll quickly run this and I'll have query representations, key representations, and value representations with me. Now the only thing that is missing for this particular formula is this particular term, which is square root of the total number of dimensions in the key matrix. So what I'll do next is I'll quickly create a query representation dimension. So basically the denominator term is what I'm trying to calculate. So query rep is equal to query rep dimension is equal to say np dot array. I'll say float query representation dk, right? So key representation dot shape of 0. So this basically gives me the total number of rows that are there into 0 raised to power 0.5, which is basically giving me the square root. And this array I want to represent as float 32. So that is what I enter here. So I'll quickly go forward and press enter here and I'll quickly run the cell. So float 32 is not defined. So I got the mistake and now this works. If I now when I show you this, it's basically 1.73, which is the square root of 3. So what I have now is I have the representations for one input set. If we now take a broader picture and look at what we've done so far, we had a set of input. We had 3 matrices, query, key, and value. we've passed all the three inputs through all the three matrices, and we have a query representation, a key representation, a value representation, and we've also calculated this particular term, which tells me the dimension of the key matrix. One thing that I've just realized is I've written query representation dimension, but I've taken key here. But the good part is the dimensions of both query and key have to be equal. So I can basically interchange this, or I can rename this to key representing dimensions as well. Anything goes. Value can have a different dimension with one condition, that the rows and columns of the final calculation match. But apart from that, query and key have to have the same dimensions in your self-attention layer. So I can change this, or I can also change this to say query representation. Anything works as long as the dimensions of both query and key are the same. So I can quickly run this and the value would still remain the same. So this is one thing that I wanted to highlight. Let me start the entire calculation by splitting the entire calculations into multiple steps. So let me start by calculating this numerator term first, which is query into key transpose. So I'll say query representations dot key representations dot transpose. So this is step 1. So I'll create a variable step 1, which will calculate this for me. Step 2 is I'll divide step 1 divided by, so this is my numerator. I want to divide it by square root of dk, which is something that I've already calculated here, which is this particular term. So I'll divide step 1 value by this particular term, which is where I'll compute the value. So step 2, if I show you the outputs as well, step 1 is basically a 3x3 array. Step 2 is again a 3x3 array, but this time you would see a scaled version of this array. So this is where we are. Now once all of this is in place, all I have to do is I have to apply softmax. So that is where my step 3 comes in. So, and rather than typing in step 3, what I can say is attention score softmax is equal to softmax of step 2, and I'll specify the axis. So I'll say axis is equal to 1, and finally I'll print out the scores. So these are my attention scores. We've not yet reached to the final attention score, so hang in there. But after the softmax, this is what we have. We have attention scores between the three inputs. So this is what you can see here. If I show you, so this is basically a 3x3 matrix, which we can assert by calling the shape function as well. Now if I look at the value representation, and if I call the shape function, it's again 3x3. So one way to kind of deal with the entire calculation going forward is I have to take the dot product to calculate the final attention scores. So say attention final is equal to the attention score softmax dot the value representations. If I do this much, I have my attention final scores. So if I show you this, these are my attention scores. A better way to represent this would be by creating a heat map. So AX is equal to SNS dot heat map attention final line width 0.5 and CMAP is equal to Y1, if I'm not wrong, GNBU. This is the one. So it was not 1, it was L. So it is my mistake. So here is where you have say a proper heat map generated with respect to attention scores. Here you have very little attention between, say, the second vector and the third vector, which is queen and mobile. Here you see that there is huge attention between queen and queen. the objective of this entire exercise is to show you how attention would work within the values that I'm using are entirely random, right? So WQ, WK and WV are something that are trainable. So these matrices are basically trained by feeding in data and then taking the error and then kind of back propagating the errors, and then this weight update happens. So what I've done in this entire exercise, I've kind of taken random values which I felt could give me some insights. And this is how you can generate heat maps to look at relationships for different, say, sentences. So this is how self-attention is working under the hood. Here what we have assumed is the value matrix is also the same, right? But there are chances that it may not be the same. There are cases wherein the value matrix can be a bit different, which is where the dot product calculation may not hold true for us. So this simple calculation that you see here, which is attention score softmax dot value representations, this may not hold true for us, which is where there's a different technique that we can try out, and we can see if the given that at this point of time query key and value matrices have the same dimension, so the values for the newer method that I'm gonna share with you, that should also turn out to be the same. So this attention final that you see here should essentially be the same once we have a different form of calculations as well. Okay. So in order to kind of show you a different set of calculation, what I'll do is I'll say weighted values. I'll create a variable called as weighted values equal to the value representation. I'll add a axis here, multiply this with attention scores. So I'll say attention scores softmax. So I think this is the one that I'm looking for. And here I'll take the transpose because I need the transposed values to be multiplied with the actual value representations. And I'll create a 3D matrix from a 2-dimensional matrix by adding a new axis here by the command none. I'll multiply and I'll have the weighted values here. So I'll quickly run this cell. The weighted value shape, which I'm guessing would be a 3-dimensional vector. So you have 3-dimensional array here, 3 cross 3. So you have 3 matrices, each has a shape of 3 cross 3. Okay. And if I show you the values, these are the 3 different matrices that are there. Now all I have to do is, if I have to calculate the attention final score, I have to sum all of them at the 0th axis. So what I mean is, the attention first value would be the sum of this particular term, and this particular term. So there are 3 matrices. I have to sum all the 3 together and get a combined sum. So the way I would do that is attention final equal to np.sum. I pass in this particular weighted values and I'll say axis is equal to 0. So attention final, say 1, I'll keep it as attention final only. And now I'll show you the attention final. The output is something that I have not removed so far. So attention final is, or wait, rather than adding, say, less confusion, I'll say attention final 2. And now when I show you the output of attention final 2, the values are 0.513 something something, which is the same as what you see here. So if I pick one random value, 7.92, which is through the previous calculation, it's also the same here, minus 4.42, minus 4.42. So the calculations are the same. You can pick and choose whichever representation you like in terms of calculating the attention final values. In cases where values dimensions are different as compared to query and key values, this approach is better as compared to the previous one, but technically you can pick and choose what you want. So this is something that I wanted to share across. I wanted to share how attention is working under the hood, and how, say for example, the higher the value, the more is the attention between that particular word and the other word that I'm considering. So this is something that I wanted to share across with all of you today. I hope you found this video informative. If you do like the content that I create on my channel, it would be super motivating if you can press the subscribe button and also press the bell icon to be notified for amazing videos on data science and machine learning. Thank you so much for watching the video.